Welcome to CrystalDiffract 7. In this tutorial we're going to demonstrate basic Rietveld refinement for lead sulfate. Rietveld refinement is essentially a curve fit, refining an existing and reasonably known starting structure relative to an experimental dataset. So we're going to need a crystal structure and an observed pattern. The observed pattern can be loaded as an XY text file, such as this one, which we can preview in the Mac Finder. And the starting structure could be loaded from a text file or a Crystal Maker document, such as this one, which we'll also preview. We'll begin by opening a new window in CrystalDiffract, and we'll add our two files by dragging and dropping them into the diffraction pane. If we show the sidebar, you'll get the two patterns listed there, and we can toggle their visibilities on and off using the checkboxes. At this stage we need to set up our simulation correctly. Now our observed data are from a constant wavelength neutron diffraction experiment. So we'll go to the diffraction menu and specify constant wavelength neutrons. Notice that the program can also handle time of flight neutrons, but that's not what we want. We want constant wavelength neutrons. We also need to set the wavelength, and we can do that using the wavelength command, and we'll type in a value of 1.909 angstroms, and this is monochromatic radiation. Having done that, we can go to the Refine inspector, and this prompts us to specify which particular patterns need to be refined. Now, document windows can hold any number of patterns, and multi-phase refinement is also an option, so we do need to tell the program which patterns are to be used. We'll tell the inspector to use our existing patterns by selecting them. You can shift-click on that second pattern. Now we need to tell the program what kind of peak profile the peak should be refined against, and we do this by going to the Setup popover and choosing the peak profile. I'm going to use pseudo void. Now looking at this observed pattern, you can see that on the right hand side things are a little bit incomplete, and we may want to cut this region out from the refinement. Let's zoom in a little bit for greater precision. And I'm going to use the arrow tool to define my minimum and maximum limits. I'm going to click and drag to the right limit and let go of the mouse, and the ruler has retained those limits. And we can transfer those to the Refine inspector by going back to the Setup popover and clicking the ruler button. Now we can hide the ruler. And now we're ready to do our refinement. Now the program lets us load refinement parameters by clicking the Load Parameters button. And quite a lot happens here. The program fits some peaks and determines some sensible starting values for the background and the peak profile. Notice that it also adds some curves to the plot, and they're listed here in the patterns list. We have a calculated profile in orange, a background in blue, a difference plot, and a refined crystal. On the right hand side, the inspector shows a list of refined parameters, and let's go through what each of these means. First up is the scale. Now we can edit this starting value, and any other parameter for that matter, simply by clicking on the numeric value and entering a new number. So let's try 150 and see how that looks. and you'll see that the orange calculated pattern has increased in value. Let's go back to 130, and it decreases in value. Now to the right of the numeric value is an actions button, and if we click that, we get a popover, which power users can use to adjust the range for the parameters variation and also a damping factor. This is in case some parameters are just a little bit too sensitive. Next up is the background group. And there are many parameters listed. These are actually the coefficients for a so-called Chebyshev polynomial. It's a complex function designed to model a wide range of background shapes. Under instrument, we have the wavelength, which we won't be refining, the zero shift, and then the peak shape parameters. And notice there's an asymmetry correction. Then we have the unit cell. And notice that alpha, beta and gamma are grayed out. They're not refinable. This is because the program takes symmetry into account, and this is an orthorhombic crystal. Alpha, beta and gamma must stay at 90 degrees, but A, B and C can vary independently of each other, so those are enabled. Next, we have our fractional coordinates for each site in the asymmetric unit. And notice that some of these coordinates correspond to special positions, Z at 3/4, for example, and these won't be changed, they're grayed out. Again, symmetry is being preserved. Moving on to displacement parameters, you can see that we have isotropic displacement parameters by default. If we click an actions button, there is a checkbox for toggling between isotropic and anisotropic, and if we do that, we get the 6 displacement parameters for this symmetric tensor, U1 to U6, with symmetry constraints. I actually want to use isotropic temperature factors, so I'll turn that one back on. And finally, we have site occupancies. Now, the program has a built-in refinement strategy to make things easier. We can click the Auto Refine button, and the program will do its best. It will start off by refining the scale factor, some of the background terms, and then gradually build up the refinement by adding the unit cell, the zero shift terms, more background terms as required, the fractional coordinates, starting with the strongest scatterers, more profile parameters, and then finally the isotropic displacement parameters. So let's click Auto Refine and see what happens. Well, first up, you can see that we have a new window, the refinement trajectory. And this plots the chi-squared value, which is the goodness of the refinement, and it's gone down, which is a good sign. You can see on the right hand side that various refinement parameters have been set. Their checkboxes have been turned on, indicating inclusion in the refinement process, but not all of those parameters have been enabled. Going back to the plot, you can see that the orange calculated profile matches the black observed pattern very nicely indeed, and our blue background is looking pretty good. Now, this was only a start, and we can continue manually by turning on parameters and running manual refinement cycles. So let's look at adding a few more terms to the background. Let's turn on B7, B8 and B9, and let's run a manual cycle. Chi-squared's gone down slightly. Maybe we can add a few more terms. And it's gone down again. Incidentally, you can undo any of these cycles by clicking on the undo button, and we go back to the previous chi-squared value, or we can redo. and we've got our lower value. Let's close the refinement trajectory window. We'll now switch to the results pane. If we expand the list, we can see the full set of refined parameters with errors given in brackets. Sometimes you may see a warning triangle, and if you hover over that, you'll see the reason for the warning. And we can export all of these parameters to a CSV file if required. So those are our refinement results. Now, in any kind of complex refinement, there are going to be correlations, and we can visualize these graphically using the correlation matrix window. Now, this is a color-coded window which shows every single parameter that's been refined plotted against all of the other parameters. And it's color-coded from red to, which means it's fully correlated, through green, minimal correlation, through to blue, anti-correlation. So the diagonal terms will always be red, and one hopes that the off-diagonal terms are green. Now, if we hover over a square, we can see the correlation listed explicitly. So here we have the background B10 term correlated with the instrument GW term, which is a peak shape parameter, and there's a 28% correlation. Such correlations could be reduced further through manual refinement cycles. At this stage, it might be useful to compare the starting structure with the final structure. And we can do this by sending the structures directly to CrystalMaker using the patterns list. We simply select each structure, hold down the Command key on the Mac or the Control key on Windows to select multiple structures, and then use the Actions menu to visualize the crystal structure. Now that will launch CrystalMaker and show each structure in a separate window. Now I'm going to display the two structures in the same window by dragging a structures list thumbnail from one window to the other. So we just need to use one window now, and if we open the structures list, we can switch between the two structures to compare them. If we hold the Shift key down, then we can superimpose the two structures, and we can see the scale of the changes that have happened during our Rietveld refinement. So this has been a quick overview of Rietveld refinement in CrystalDiffract 7.